If you look at these different representations of Earth's magnetic field, there's something in common with all of them that is very wrong on a scientific level. So it's not the way that the magnetic field actually goes. And so I just want you to take a moment and think about what that might be. So we're just going to pause for a moment, look at all three of them, and just think about what is wrong with them. Okay, so now what I wanted to do is I wanted to kind of introduce a piece of equipment for exploring this topic. And so what we're going to be using is magnetic field sensor and a positional thing. So it'll find the different magnetic fields at different positions, and we'll just use that in order to inquire about this question about what is wrong with those diagrams. So this is the measurement we get from just open space. This is Earth's magnetic field. And so as you might notice, it is pointed towards the ground. And just to be clear, this was not taken at the North Pole. It was taken in Canada. So the magnetic field is going into the ground in Canada. So now we can look at the bad representation versus the good representation of Earth's magnetic field. Oftentimes they will have a diagram like this, which will show that all of the magnetic field travel exactly north. And so this is inaccurate because magnetic field travel down into the Earth much sooner than the actual North Pole. The other inaccuracy that often comes up with these diagrams is that they show that the North Pole is actually a magnetic North Pole, which is one of those things is a little bit of a weird linguistic thing that came up. So magnets, as we all know, opposites attract. When magnets were first being created, they were defined from the actual local magnet. So in your local magnet, the local North Pole will point towards the north. But that actually means that the North Pole is a magnetic South Pole. So that's a little bit of a confusing thing, and it's oftentimes misrepresented in diagrams. They'll often show that the North Pole is the North Pole of a magnet when it's actually the South Pole, because the North Pole of your compass points towards the South Pole at the North Pole, which is a little bit of a weird naming convention. So an extra question might now arise on why do compasses actually point towards the North Pole? The reason why compasses still work is because you're doing a projection onto the tangent. When you're holding out a compass, because it's not allowed to travel downwards, it'll end up traveling perpendicular to the direction that you're holding it. So it's really neat to just be able to look at the magnetic field. It's something that you often don't get to see. You read a lot of books about it, but it's sometimes hard to actually visualize. And so it's really neat to get to see that. And one thing that's kind of neat is to look at different objects and how magnetic fields move around those objects. So all objects on Earth are surrounded in Earth's magnetic field, and a lot of them have interactions with that magnetic field. And so if you move this device by different sets of objects, you'll notice that they will deflect the magnetic fields a small amount. And so it's interesting to look at that. One thing that you should actually be able to do with the magnetometer and this positional information is you should be able to create a metal detector, which is a neat little application that you can put together. So now that we've done some learning from our app, I kind of wanted to show you quickly how it was put together, because it's actually a very simple process and you can kind of put it together yourself and make some edits to it if you wanted to as well. So everything is up on GitHub. Here is the address. And now we're just going to go into a quick run over the code and what's happening. One thing that comes up with using a magnetic sensor through a web platform is it's a little bit unsecure. So one thing that's really, it seems a little bit fantastical, but you actually can capture what the CPU usage is with a magnetometer on your cell phone. Chrome has been thoughtful in advance, and they have some security flags that we have to get rid of in order to actually make this project work. Okay, so to start off with, we are going to call the magnetometer API, and we'll call it mag sensor, and then we'll also have a magnetic background that will just initialize to be 0. Next up, we have to call a function in our on session starts. So this will be called when our AR session starts, and then we'll add an event listener to the mag sensor, and then we will start it. Within the event listener, every time it does a reading, what we need to save that measurement. So we will save that as a local measure, but the local measure is not actually local quite yet. So we need to get the target quaternion from the camera. Then we need to apply that quaternion. So this is turning our local measurement that was measured from the phone and converting it into the reference frame of our local area. So this is actually a really important step to just focus on for a moment. So you can do this to convert something from your phone's reference frame into the local reference frame. So it's just applying the quaternion of the camera. And so it's a really simple step, but like a lot of the magic happens here. So we're just gonna pause on this for a moment, take a moment to highlight how important this step is. Okay, so after that, we're going to need to get the length of the magnetic field. So we're just going to do a measure, and then we're going to scale it by 1,000. And then what we're going to do is we're going to make an arrow. Okay, so just going through the different things that we're handing this arrow helper, we're going to be giving it the direction, so that's the first thing. The position, that's the second thing. The third thing is the magnitude. After that, we're going to be giving it a color. And then we are going to be adding it to the scene. So this is the yellow arrows that we were seeing. Those are all the information that it gets. Finally, I wanted to discuss how we would remove the background. So right now there is the Earth's magnetic field that's going through all of this, and so we want to be able to get rid of that so that we can only see local measurements. And so how we do that is we just record the first few measurements, and then we will take an average of that, and we'll just vector subtract out that from all of our values.